Let's talk about implicit differentiation. In this video, I'm going to do a few solutions on the implicit differentiation worksheet. So I'm going to do 1A, 1B, and 2C in this video. All right, so if we start off with 1A, we're given an implicitly defined curve and asked to find a formula for its derivative, dy dx. And we always want to give our answer as a function of x and y, meaning we want to solve for dy dx equals as our final answer. Okay, so if we have x cubed plus y cubed equals 9x, then we're not going to rearrange or anything. We're just going to differentiate both sides with respect to x. So we're going to do d dx of this equals d dx of that. So this notation d dx, it means the derivative of what's in the parentheses, but specifically it's saying like treating x as the input variable. So the derivative of x cubed is the 3x squared that it's always been. But for y cubed, we have to treat this like a chain rule. So the outer operation is the cube. So we still have 3y squared. But then it'll be times the derivative of the inside function, which is just y. So we end up with times dy dx, essentially at the end, kind of multiplied onto the end of any derivative that has a y in it instead of an x. And then on the other side, the derivative of 9x is a regular 9. All right, so we've done the differentiation step, and now all the rest of the problem is satisfying this requirement. We want to solve algebraically for dy dx. So in this one, it's the simple case where there's 1 dy dx. So I'm going to subtract 3x squared to the right-hand side. And then I'll divide both sides by 3y squared so that dy dx is alone. So I get 9 minus 3x squared over 3y squared. Or all three of the terms here are divisible by 3. So I could simplify this by dividing everything by 3, and I get 3 minus x squared over y squared. All right, so part B of this question says find the equation of the tangent line to this same curve at the point 1, 2. So notice when x is 1 and y is 2, they really do satisfy this curve here, right? Because I would have 1 cubed plus 2 cubed is 9, and that equals 9 times 1. Okay, so for the tangent line, we need the xy point, which we have here, and then we also need the derivative of the function at this point. So we're going to plug this 1 and 2 in for x and y here in our formula for the derivative. So the slope of my tangent line is dy dx at x equals 1, y equals 2. So that gives me 3 minus 1 squared over 2 squared. Right, and then I'll simplify carefully. 3 minus 1 over 4. That's 2 over 4 is 1/2. Okay, so now I just want to put together the equation of a straight line that goes through the point 1, 2 and has a slope 1/2. If we do it in point slope form, I'll have y minus the y value equals the slope times x minus the x value. Or if you want to do it in mx plus b form, we could kind of take some extra steps here. Distribute the 1/2 into the parentheses, and then add this 2 onto the right-hand side. So that would give us y equals 1/2 x minus 1/2 plus 2 is going to be plus 3 over 2. Okay, let's turn on to the back page of this worksheet and do another example that has the same agenda as part A here, but is a much more complicated differentiation step. Okay, so this is 2C on the same worksheet. Our agenda here is to compute dy dx, and we always want to give our answer as dy dx equals a formula of x and y, so there'll be a lot of algebra and solving for it here. Okay, so if this equals that, the derivative of this equals the derivative of that, so that's my first step. On the left-hand side, the derivative of 2 to the x, I'm just kind of going to denote here, I'm taking the derivative with respect to x. The derivative of 2 to the x is 2 to the x ln of 2. For 3 to the y, I use the same derivative rule, 3 to the y ln of 3, but because x is the actual input variable, this gets times dy dx, just like the 3y squared in the previous example. Now, the derivative on the right-hand side is really complicated. So we're going to take this off to the side and do some scratch work. All right, so this requires a chain rule. This is composition f of g of x, where the f is e to the x, and the g is x squared y. All right, so if I plugged this in for x in this expression, I would have e to the x squared y. E to the x's derivative, we know, is itself. And then when we go to do the derivative of x squared y, it's a product rule. One piece is x squared, and the other piece is the y. All right, so x squared's derivative is a normal 2x. When I go to do y's derivative, I would say 1, but since x is the input variable, I'll say 1 dy dx, or rather just a plain dy dx. Okay, so all of this was to get me the derivative of x squared y. So I'll take these 4 red pieces and do the product rule formula with them. So that'll be f prime g plus g prime f. F prime g plus g prime f. Okay, and now all of this, the blue parts, were for the original chain rule. So I'll take the blue stuff and now do the chain rule formula for my overall derivative, f prime of g times g prime. And I'm going to put it directly into my right-hand side over here. So f prime of g times g prime. And that's my derivative step. So the rest of the work here will be us algebraically solving for dy dx. Now I can see there's 2 dy dx's in this equation, in this term right here, and in this term right here. This one is the troublemaker, right? Because the dy dx is kind of buried in this set of parentheses that we had to have there, but it means that I couldn't factor dy dx out of all of this. So what I need to do before any other steps is distribute e to the x squared y into these parentheses so that we have e to the x squared y times this plus e to the x squared y times this, and then I'll have a dy dx term that I can manage. All right, so my left-hand side will stay exactly the same. On the right-hand side, I have e to the x squared y times 2xy plus e to the x squared y times dy dx x squared. So this distributed to each of these pieces. Now, the reason this was helpful is that now this term right here is one that if I put it next to this term, I could factor dy dx out, and then I'm one step away from finishing. All right, so I want to get these 2 terms alone together on either side of the equal sign. It doesn't matter which side. And once they're alone together, I can factor that dy dx. Okay, so why don't we put the dy dx terms on the right-hand side? It doesn't really matter what you pick. So if I want them both on the right-hand side, this one stays. This term I'm going to subtract to the right-hand side, so it ends up over here. And then this term I'm going to subtract to the left-hand side so that it's over here with 2x ln of 2. All right, so 2 to the x ln of 2 is still here. This is gone, but this one has showed up. So I have minus e to the x squared 2xy. Now on the right-hand side, this is gone, but this one's still here. So this term is still here, and then it's minus this term that has come over from the left. Do a quick double check. Make sure I haven't lost any terms. I started with 4, I still have 4. And now on the right-hand side, I can factor it out. So all this is the same. On the right, I have dy dx, and then a big set of parentheses, both of these terms with their dy dx pulled out. So I have just e to the x squared y times x squared minus 3 to the y ln of 3. And now my final step to solve for dy dx is to just divide both sides by everything in these parentheses. So I'll have the original left-hand side as my numerator. And then divided by everything in these parentheses. That is my final answer for the derivative in 2C.